Hey, everybody, and welcome to 6-2 Real Application of Normal Distributions. I think this is a pretty quick section. We'll go over a few things and then we'll do some problems. Okay, so this section presents methods for working with normal distributions that are not standard. Standard, remember, was the mean is 0. So here the mean is not 0. And it could be the standard deviation is not 1, or both of those could be true. So the key is that we use a simple conversion that allows us to standardize any normal distribution so that the same methods of the previous section can be used. So basically, to do that, we have a formula. There's our formula. Z equals X. X is the value that you're using to find the probabilities. And I will, of course, do an example. This formula allows us to standardize any normal distribution so that the X values can be transformed to Z values, to Z scores. So basically, let's say you start off with a normal curve and our mean is, let's say it's 100. And our standard deviation, so let's say mu equals 100, and our standard deviations equal to 5. Well, we can plug in that formula, and we can say our Z number is equal to some X minus 100 divided by 5. So let's say I want to find values of X. I want to find any value where I want to find the probability that X is less than. So let's make X equal 110. And the problem will state what X is. So we would have Z equals 110 minus 100 divided by 5, which is 10 over 5, which is 2. Now, I've now made it our Z number of 2, which means we're 2 standard deviations away from the mean. So this would be 2 standard deviations, right? Which is true because my standard deviation is 5, and I picked 110 for X. So 1 standard deviation would make it 105. 2 standard deviations would make it 110. So perfect. So we normalized it, okay? So it says here, what proportion of men are taller than the 72-inch height requirements for shower heads? Heights of men are normally distributed with a mean of, so let's use our StatCrunch. All right, so I move things around. So I have stat, calculators, normal. And in here, it just comes up with mean is 0 and standard deviation is 1. I could change it into a Z-score, but I don't need to because I can just change this to the mean is 68.6. The standard deviation is 2.8. And I'm looking to find the percentage of men who are taller than the shower head. And the shower head is 72 inches. And now this is the percentage of men, or this is not the percentage, this is the probability that men are greater than 72 inches tall, which is exactly what we're getting here, 0.1123. So we got our answer. And then what we want to do is, well, we could also convert it to 72 inches to the Z-score by using Z equals X. X is 72 minus mu, which is 68.6, divided by 2.8. That would give me a Z-score of 1.21. So, all right, so now if I just use our regular calculator with the mean equals 0, standard deviation of 1, And what we want to find, we converted the z-score to 1.21. And we hit compute. Notice that's a little bit off from what we had before, which is 0.1123 or 11.23%. But it's because we rounded to 2 decimal places. If I use the number that I get and don't round it to 2 decimal places and put in the actual value, notice we get the 0.1123, which is 11.23%. So it just depends on how you feel more comfortable. So you could do it either way. You can convert to a Z, or you can just put in, using StatCrunch, we don't need to convert it, is what I'm trying to say. All right, so the interpretation. The proportion of men taller than 72 inches is 0.1123. Multiply that by 100 and you get 11.23%, which means that about 11% of men may find the design to be unsuitable. Okay? So finding values from known areas. Here are some helpful hints for those cases in which the area or probability or percentage is known, and you must find the relevant value that goes with it. So graphs are extremely helpful in visualizing, understanding, and successfully working with normal probability distributions. So they should always be used. Don't confuse z-scores and area. So for example, let's say I have a normal curve, and these numbers down here on the on the horizontal axis are my z-scores. Let's say this is 1, 2, -1, -2. So this is also mu, and this is where z equals 0. So mu and z equals mu equals 0. And then here we have sigma is equal to 1. We've made it so that our mean is 0 and our standard deviation is 1 by converting to a z-score, if that's what we're doing. So that's what this is saying. This is saying z-scores are distances along the horizontal scale, which is what I just showed you. But areas, so for example, if I wanted to know the probability that my value is less than or equal to 1, then it might be too dark, let's see. Then I would highlight all this. This is my area from all the way to the left to the value that I picked for my z-score. Here I picked 1. So if I say x is less than or equal to 1, I would get the area right there. And that area, so in here is the area, which is the same as the probability. So it is not the same as the z-score. Okay? We could even find out what it is. Let's see. Let's pull up our StatCrunch. And now we've normalized it. So we made mean is 0, standard deviation is 1. I want to find x is less than or equal to 1. I hit compute and I get my answer, which is for this particular problem is 84.13. So my probability is 0.8413. 3, which, or I can say it's 84.13%. Now, I didn't apply it to anything, but I want you to see the difference. This is the probability, is the area under the curve. And on StatCrunch, hold on StatCrunch, that number is, so the probability goes in here. This is the probability. This is my z-score. If I wanted to know the probability that it's greater than 1, now notice it's highlighting the other side, and this would be 1 minus 0.8413. So that's basically how we're looking at it. The area in red is the probability, and the z-score is here at the bottom. Okay. But areas or regions under the normal curve, that's what I just said. You probably won't be using a table. List the z-scores in the left column and across the bottom row, but areas are found in the body of the table. I think I showed you the z-scores, the z-score tables in the last video, so I don't think there's any point in bringing that back up, but I don't think you're going to be using them anyway. But it is important to know what the differences are. So we have to choose the correct left or right side of the graph. So if it says a graph separating the top 10% from the others will be located on the right side. Basically, what we're saying is, erase this, and let me change this. So if I bring back my StatCrunch, okay, so let's see. So it says, choose the correct side, right, left side of the graph. A value separating the top 10% from the others. So I want to know what value separates the top 10%. So here, I don't know the z, but I know the probability is 10%, which would go in here. This would give me my z-score. Okay, so that's my z-score. Let me see, I'm going to move this and this a little bit so we can read this. There we go. Okay, so that's my z-score that separates the top 10% from the others. Will be located on the right side of the graph. That's what it's saying. But a value separating the bottom 10%. Now I hit less than, and I say the bottom 10%. This is going to be the same number, notice, except it's negative. So at negative 1.28. Positive 1.28. They're the same z-score, one's positive and one's negative. Okay, so that's an important piece. Anything, I can't write on that, hold on. Anything less than the middle here, which is our mean, or our z equals 0, anything less than, these are all negative scores. These are all positive z-scores. Okay, I think that makes sense. A z-score must be negative whenever it is located in the left half of the normal distribution. That's what I just said, because remember, our normal distribution looks like this. Here's the mean. So this way are negative z-scores. And from here this way are positive z-scores. areas or probabilities are always between 0 and 1, and they are never negative. This is very important. So, and I know we've talked about this many times, they're always between 0 and 1. They're not going to be negative because they're areas, okay? So basically the area is whatever part of the curve you want. This is less than or equal to some number, or I can make it, this is greater than or equal to some number. Okay. I think we've done this enough. I think you understand. I'm going to do some example problems as well. Don't worry. Okay. Procedure for finding values from known areas or probabilities. So we would sketch a normal distribution curve, enter the given probability or percentage into the appropriate region of the graph, and identify the X value being sought. So that is basically you want to find whatever there, you're going to be given some X value that you want to find. Okay. And if you know the Z number, so there, we have to know the Z number, we have to know the standard deviation, and we have to know the mean. And remember, our formula was Z equals X minus mu over sigma. Now, I'm going to just do a tiny bit of algebra. If you get scared, don't get scared. You don't have to, you can memorize this formula, you can write this down, but I'm going to, if you do know algebra, you'll know what I'm doing. I'm going to multiply both sides by sigma. Okay, so now that's multiplication. And this sigma would cancel with this sigma. So my next line would be sigma times Z is equal to X minus mu. And if I want to solve for X, I just add mu to both sides, right? So that would give me mu plus, I'll write it the way they have it, Z times sigma equals X. Same formula, but we have different information, so we're using it a different way. Okay. Let's see, if you know the Z-score, must convert it. I just showed you. Refer to the sketch of the curve to verify the solution makes sense in the context of the graph and in the context of the problem. This is something that you should always get into the habit of anytime you're doing word problems, because sometimes people write things down that don't make any sense. It's either because they don't know how to do the problem, obviously, and so they get the wrong value, or they don't even understand what kind of value they should get. So for example, if you got a probability that was greater than 1 or less than 0, we would obviously know that's wrong. There's many times that you'll know that the probabilities that you're getting are not correct. And just think about your answers and see, I'm not saying do it over and over again, just think about your answers and does it seem logical, okay? Like for example, with this example that we did back here with the shower, well, proportion of men that are taller than 72 inches, well, that's 6 feet tall. So 11.23%, that makes sense, right? There's people that are shorter than 6 foot tall. There's people that are taller than 6 foot tall. But we're saying here, given all the other information that we have, that 11.23% of men are taller than 72 inches. Okay, so let's read through this question. When designing equipment, one common criteria is to use a design that accommodates 95% of the population. We have seen that only 46% of women satisfy the height requirements for U.S. Air Force pilots, probably because they were set up for men. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest 95% of women to be pilots? That is, find the 95th percentile of women, of heights of women. Okay, so I'm gonna put this on, oh, put this on one side, hold on. It's on one side, get my StatCrunch open on the other side. To my normal calculator, and let's just open this up so we can see it. Okay, here we go. So our mean is 63.7. Our standard deviation is 2.9. We want to know the value, which we don't know, where the probability is less than 0.95. I hit compute and I get 68.47. So that's the height, that's the maximum height that a woman can be, or that the Air Force can set the maximum height of a woman to 68.47. And that would allow them to accept 95% of women. Okay, and let's see if we got the right answer. Oh, 68.47 and 68.47. It's right there. We could have converted it to a z-score, and then we could have found it, but why, right? So basically the area of 0.95, that's what I put over here on the right side, corresponds to a z-score of 1.645. That's if I leave the mean to be 0 and the standard deviation to be 1. Then I could use my formula, put in all the values, and I would end up with x equals this value, which is, I guess I didn't put it in, so it's 1.645 times 2.9 plus 63.7, which equals, this equals 68.4705, which is, I'm pretty close. I mean, this is a little different than the value that we got here, but close enough. So we found x using StatCrunch, or we can find x using that formula. Okay, and that really ends this part. Let me bring up the problems that I selected. Let's see if it's still active. Yeah, it looks like it's still active. So again, I have my normal calculator. I'm going to well, I can close it and just reopen it. That'll help also remind you where it is. Stat, calculators, normal. And this is where we start. Here it says, find the area of the region, of the shaded region, for the graph to the right, which depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So I could convert it to a z-score, or I can just put it in like this. And I actually want, notice it's between two numbers, so I'm going to put this as between, and my lower limit is 106. My upper limit is 128, and I hit compute. I get how many decimal places? 4 decimal places. Got it. Copying it and pasting it in, and there it is. So pretty easy, right? Okay, find the indicated IQ score. The graph to the right depicts IQ scores of adults, and those scores are normally distributed. We have the same mean and standard deviation, and we want to find X. And we know that our probability which is the same as the area that this, under this curve, which they're telling us is 0.8. So we want standard, we want X is going to be greater than some value, and the value is 0.8. And we hit compute, and this is our IQ score, and we want to round it to 1 decimal place. So that would be 87.4. And we check answer. Perfect. Okay, let's do another example. Engineers want to design seats in a commercial aircraft so they are wide enough to fit 90% of all males. Accommodating 100% of males would require very wide seats that would be much too expensive. Men have hip breadths, which I guess are the widths, that are normally distributed with a mean of 14.7 and a standard deviation of 0.9. Find the P of 90. That is, we want to find the hip breadth for men that separate the smallest 90% from the largest 10%. So if I want to separate the lower 90% from the largest 10%, I can say less than 0.9. And I get this value, okay? And that's to 1 decimal place, so it'd be 15.9. Or I can say, because it says the smallest 90% from the largest 10%, I can say greater than 0.1. Actually, it did it for me without me having to do anything. And when I hit compute, I get the same z-score. I get the same value, not z-score, for X. So either way, that should be the answer. Let's hit check. Perfect. And then let's see what this is. Suppose that the sitting back to knee length for a group of adults has a normal distribution with a mean of 24.2 and a standard deviation of 1.1. These data are often used in the design of different seats, including aircraft seats, train seats, theater seats, and classroom seats. Instead of using 0.05 for identifying significant values, we're going to use the criteria that a value X is significantly high if the probability of that value or greater is less than or equal to 0.1. So we're going to find the value or greater at 0.01 is, yes, I changed it. So here we have back to knee lengths greater than, not this, because this is where I want my stopping. That's the biggest number I want it to be. I want it to be less than 26.8. And then here, I'm going to say the lower 1%. I hit compute. Probably that. And I get to 1 decimal place, 21.6. And so basically I'm saying it has to be bigger than 21.6 and smaller than 26.8. So we really want the area, and let's say our largest value was, what is it, 26.8. So we want the value that I'm coloring in yellow. And let's say 26.8 is right about there, okay? So we want this area that is in yellow. So it's really between two things, but since I only have one box for the probability, I have to do it a little differently. I can't do it all at once. Okay, but this, now let me just finish. This is the area that we're talking about. From there to approximately here. And in red is the part that I do not want, right? I want the yellow. And that's what this gives me. It actually gives me the probability was this is, so this probability here, this probability here is 0.01. And this probability here is 0.01, which is the same as the area on both sides under the curve in red. We don't want the part in red. We just want the part in yellow. Let's hit check. Perfect. All right. Now it says, using this criteria, is a back to knee length of 26.4 inches significantly high? Well, 26.4, let's say it's somewhere right around here. Okay, which means that, is it in the critical region or is it in the region that we're looking for? So this is not significantly high because it is inside the range of values that are not considered significant. Out here, hold on. Out here, this is significant. And this is significant. The red is significant. The yellow is not significant. So it falls inside. We hit check. And we did it. All right, so I pulled up another of the same question because I wanted to show you another way you could do this. So I'm gonna get StatCrunch back up again. Well, actually, let me get StatCrunch first. Okay, so suppose that the sitting back to knee length's really the same, it'll probably have different numbers. So I'm going to go to Stat Calculators Normal because this has a normal distribution. And I just wanted to show you one other way. So we have a mean of 24.8 and a standard deviation of 1.2. And it says, these data are often used in the design of different seats, including aircraft seats, train seats, theater seats, and classroom seats. Instead of using 0.05 for identifying significant values, use the criteria that is a value X is significantly high if P of X or greater is less than or equal to 0.01, and a value is significantly low if P of X or less is less than or equal to 0.01. Really similar to the last question, but I wanted to show you another way. Hold on. Okay, so we're doing kind of the same thing, but here's my normal curve. And remember, I want this area to be 0.01, and I want this area to be 0.01. But really, what I want to know is this part in the middle here, right? So I really want to know this what is in here. Okay, and I need to find the endpoints. So what I can do is if I have 0.01 and I add 0.01, I get 0.02. So 0.02 is really the part I don't want, right? I would call this the red area. So the red area I do not want. But this graph is symmetric. So if I say that I want, basically what I want is 1 minus 0.02, which is equal to 0.98. I want this area, don't I? And I want to know what numbers bound that area. So I can use between. And here it's going to be between, no, sorry. I know the probability. I don't know what the numbers are, so I'm going to put 0.98. Since it's symmetric, it's going to always take the middle and take the 0.01 off of each side. I hit compute, and now I have the back to knee lengths are greater than, well, this is going to be the smallest value, right? And this is to 1 decimal place, so it's 22 inches. And less than, and it's going to 27.6. And let's check that answer. Perfect. So that's a little bit easier than doing each one of them separately, I believe. I think doing each one of them separately was a little more, well, maybe not. I was going to say it was a little more clear, but this might even be more clear. And so now a back to knee length of 27 inches. So is 27 inches is actually between 22 and 27.6. So is not significantly high because it is inside the range of values that are not considered significant. Anything in here is not significant. These ends are the significant part. Let's check. Perfect. And so I think this might be a little bit easier way for you to do that last problem. I think there's something like this in your homework, not exactly the same. Okay, thanks a lot. Have a good one.